Good morning, everyone. So, let's begin with the session. I hope I'm audible to you properly, and even my screen is visible to all of you. So, how are you all? Reply me back quickly if you're able to listen to me carefully. If you can listen to me properly, and if my screen is visible to you. Okay, that's great. Thank you so much. So, uh, last in the last session, we have talked mainly about the say semiconductors. Like I can say, we talked about mainly say regarding semiconductor physics. So what all things which we learned. So in the previous session, we almost learned the concepts of conductivity, resistivity. Then we have moved our discussion and we talked about say conductivity in terms of intrinsic semiconductor, conductivity in terms of the extrinsic semiconductor, and even we have discussed what happens as temperature changes in case of the extrinsic semiconductor as well as intrinsic semiconductor. So just let me know one thing. If we increase temperature, then do you know effect on the Fermi level? Okay, so we'll come to that point. We'll come to that point. So if we talk about say a concept of conductivity and resistivity, so what we have seen as temperature increases, percentage change in majority charge carrier would be negligible. But as the temperature increases, percentage change in the minority charge carrier concentration, it would be really very high. And that's why whenever we talk about even generation rate after say with the illumination, then even we talk about say minority charge carrier instead of the majority charge carrier over there. So even yesterday we discussed about the drift and the diffusion phenomena, and we have seen quite a good example of say generation rate. So I hope the concepts are clear to you. Ki how generation take place when we illuminate a semiconductor, and what would happen to the minority charge carrier when we turn off the light, right? So if you know all these concepts, then we can move ahead with the new topic today, and that is diode. It is a really very important topic which in terms of the gate examination. So let's discuss this first. So first of all, I am going to recall you some of the concepts, some of the formulas, and some of the theories which would require to solve questions on the diode, right? The same idea would go for even Mos Capacitor also. So let's begin this. So what I must, what I know, or even what I can assume, you know basics of diode. You know basics of diode, and if you talk about basics of diode, so in that case, you know how the energy band, how depletion region is going to be created, how region is created over there, and how positive and negative charges are going to be available around the junction. So we just go through the quick revision of all these concepts. So let's begin with the concepts. So if we talk about the concepts, then the thing is the very first concept is we talk about say unbiased diode. So if you talk about say unbiased diode, so in unbiased diodes, what we are having? So in unbiased diode, we know that we have P material, we have N material. So because of initial carrier imbalance, what would happen? Holes would diffuse from P type to N, and electrons would diffuse from N type to P region, leaving behind negative immobile ions in the P region and positive immobile ions in the N region. This would occur. This phenomenon is going to occur around the junction, which means negative charge is going to be piled up near the junction in the P side region, and positive charge is going to be accumulated, I may say piled up near the region around the junction in N region. Now, what do we know? We know Gauss law. Gauss says whenever there is a charge, there would be an electrical field, and that electrical field is given by 1 by epsilon integration of charge over distance. So if we integrate this charge distribution, then by integrating charge distribution, we would be able to get electrical field inside the diode. Now what we consider over here, if we integrate this charge distribution inside the diode, that integration is maximum at the junction, right or wrong? Right or wrong? if we integrate this charge distribution inside the diode from any of the side, maybe from the P side to N side or from N side to P side, but whenever we integrate this charge distribution, then electrical field is a maximum at the junction, right? Now, what kind of questions gate can ask from here? So gate can ask questions about the negative, total negative charge inside the N region. These are the questions which has been already asked in gate. So if I talk about say depletion region, so in case of the depletion region, we have total depletion width of XD. Depletion width, I can say depletion region's width in the P region is XP, and depletion region's width in the N region is the XN. So now what do we know? What do we know? We know that per centimeter cube, this charge concentration is uniform, and that uniform charge is given as QNA. This uniform charge is given as QNA, which is obviously negative. And if we talk about say for the N-type material, then for the N-type material, this charge is what? It is uniform, which is Q and D. But we know that this charge is per centimeter cube, right? We know that this charge is per centimeter cube, and that's why to find a charge, I can say a charge inside a diode can be considered as a seed charge. So we need to just multiply distance. So to remember this formula, it is quite logical if you remember this formulas logically, which means if we talk about say negative immobile ions, then they are going to be available because of removal of holes, and positive immobile ions, they are available because of the removal of electrons from the region near the junction. And that's why what do we know? We have uniform doping in P region, we have uniform doping in N region, and that's why we have QNA and QND charge per centimeter cube, a volume charge inside P-type region and the N-type region around the junction. But if we want to find this per centimeter, like if we consider this charge to be as a sheet charge, in that case, we need to multiply this with the depletion width in both the regions, and that's why we are going to get the total negative and total positive charge in P-type and N-type region as minus QNA XP and QND XN, right? But remember one thing, that both the charges, negative charge as well as positive charge, they both are equal. They both are equal because it is unbiased diode. It is unbiased diode, and that's why if we consider this both the charges to be equal, and hence we have a well-known equation for diode which says NaXP is equal to NdXn, right? Let's move ahead. So the thing which I have told to you, that if we have charge distribution inside the material, then we definitely have electrical field, and electrical field is going to be evaluated by integrating charge distribution over there, and that's why magnitude of the electrical field is given by 1 by epsilon silicon integration of charge dx. Now if we integrate charge over here, so what we are going to get? Ultimately we are going to get area inside the curve. So area inside the curve would be again QNA XP or QND XN. So to find the maximum electrical field, we may have an equation which is QNA XP upon epsilon silicon, or we can have QND XN epsilon silicon, right? Are you able to recall all these concepts? Are you able to recall these concepts? Hello? Are you able to recall these concepts? Just reply me back quickly so that I would be able to catch this. Good. MS Priya, thank you so much. So I think, okay, Rajasekhara, I think it's you are able to recall all these concepts, right? Now, if I talk about, say, a built-in potential, then how we are going to get the value of a built-in potential? Then what do we know? Ultimately, if we integrate electrical field, then integration of electrical field is going to give us the built-in potential. So what we consider VBI, it would be equal to half of Emax into XD. So what I am telling you, if you are recalling all the equations, then no need to there is a very big formula of depletion width as well as Emax. So what I am telling you, no need to remember both of our formulas. with the help of just one formula, you can find out the quantities. Which means if you remember depletion width formula, which is root of twice epsilon silicon VBI upon Q into 1 upon Na plus 1 upon Nd, it is more than sufficient. By using this formula, even you can find out Emax by considering this equation, which is VBI is equal to 1/2 Emax into XT, right? Is it clear to you? So no need to remember both the Bhanu, good morning. It is not required to remember both the equations like Emax as well as XD, right? So I think XD, it is root of twice of epsilon silicon VBI upon Q into 1 upon Na plus 1 upon Nd, and VBI is equal to 1/2 Emax into XD, right? No, Bhanu, there is no problem. If you are late, then also I have just recalled concepts of diode, so you can catch up. So if we talk about say VBI, it's 1/2 Emax XD. So even what do we know? We can find out VBI. Yes, we find out VBI. So VBI is given as VT ln Na Nd upon Ni square. It is again a well-known equation, right? So are you able to catch all these concepts? Are you able to catch all these concepts? Right? Good. I think you are able to catch all these concepts. So now my next question to you is, if I talk about say for the P plus N, if I talk about for the P plus N material, then what do you think for the P plus N material, depletion width is high in which region? If I talk about P plus N region, then P plus N diode, then just let me know depletion width would be more in which region? Is it more in XP or is it more in the XN? XP would be larger or XN would be larger? Good, Supriya. If we talk about say P plus N material, then we have depletion width in an N region which is higher, right? But now my question is, if I give you a graph, of an electrical field, so just let me know till now what you have got. So if I talk about say graph of an electrical field, so just let me know if I draw a graph something like this, electrical field inside the material, inside the diode, then just let me know what will happen. Which kind of material is this? Can you identify this? Let's identify which kind of diode is this. Is it a PN junction diode? Is it P plus N junction diode? Is it PN plus diode? Which kind of diode is this? Can you identify this? Is it PN junction diode, or it is P plus N junction diode, or it is NP plus diode? What can you comment from this? MS Priya. I'm just asking you, is it with a sign also? Let me know what is the option. It is option A, it is option B, it is option C. So just let me know which option is correct over here. Good. Srinivasa, Supriya, excellent. It is N plus P diode, right? It is N plus P diode. Excellent. Good. So I think it's clear to you. So now let's move ahead with the next concept, which says forward biasing of the diode. Now if I forward bias the PN junction diode, then what would happen to the depletion width? Now if I forward bias the diode, then what would happen to its depletion width? Its depletion width reduces, its internal electrical field reduces, and hence we have a new internal electrical field which is reduced version of the initial electrical field. But how can we measure that? Again, to measure that, we can go for the depletion width which is new depletion width is given by root of twice of epsilon silicon VBI minus VF upon Q into 1 upon Na plus 1 upon Nd. But here important equations are how much holes are injected from P to P, P to N, and how much excess electrons are injected from N to P. These two equations play a very important role while defining the current in the forward bias condition. So I hope you must be knowing both of these equations. Excess holes injected from P to N and excess electrons injected from N to P. So I hope you know both of these equations, where delta P is given as initial concentration of holes in N-type material into E raised to applied voltage upon Vt minus 1, and delta N is given by initial concentration of electrons in the P side in a P region into E raised to Vf upon Vt minus 1. And what do we know? Around the region near the junction, we have current which is mainly because of the diffusion phenomenon, and that's why we can also find Jp diffusion as well as Jn diffusion around the region near the junction, which is dominating, and it is ultimately your total current which is going to flow inside the diode. So if we talk about, say, diffusion current, so we have an equation of a diffusion current which is dpq delta P by delta X. We have talked about delta P over here, where delta P is equal to initial holes in N material into E raised to Vf upon Vt minus 1. Delta X can be considered as average diffusion length Lp, and what do we know? Lp is given as root of dp tau p. If we simplify this, then we have hole current. We have current because of the hole. I may say not current density because of the moment of the holes, moment of the excess holes which have injected from P to N. Are you able to recall this? No need to mug up any of the expressions. All the expressions are logical, and I am telling you the logics of each and every equation, from where that equation has arisen, and how in the easier manner we can recall and remember all these equations. Is it clear to you? And in the same manner, we can even consider the Jn diffusion, equation of Jn diffusion, which would be again same dn cube np naught E raised to Vf upon Vt minus 1 upon average diffusion of electrons. But can anyone tell me, if I consider Jn diffusion, current density of electrons and current density of holes, then can anyone tell me this average diffusion length of electrons Ln, it should be in which region? If we talk about Ln, then Ln, it should be in which region? It should be in N region, it should be in the P region. What do you think? Or even if we talk about this tau n, or if we talk about even we can represent dn in terms of mu n. Great. If we talk about Jn diffusion, then all these parameters, diffusion, average diffusion length of electrons, average lifetime of electrons, mobility of electrons, all these parameters must be inside the P region, because it must be clear to you that electrons are injected from N-type region to the P-type region. That means now electron is not in P region, not in N region. Right now it is in the P region. In the same manner, if we talk about the holes, then holes are injected from P to N, which means now holes are in N region. So when we calculate current, then we need to have holes, mobility of holes, average lifetime of the holes, average diffusion length of the holes in the N region, not in the P region. Right? Is it clear to you? All the parameters, is it clear to you? And because of this also, this only, we would be having a total current density, or I can say total current inside the diode, which is given as what equation which we have known. It's a well-known equation, which is I naught E raised to Vf upon Vt minus 1 for the diode, where I naught is it's a really big equation, but sometimes in online test series you will find out I naught. But I have told you how to find out or how to remember I naught. How to remember I naught? I have told you how to remember this I naught. It is basically nothing but the diffusion current, diffusion of holes and diffusion of electrons. So if you remember this in like that, in that manner, so it would be easier for you to recall this equation. So are you following this? Are you following this? Is it clear to you? Is it clear to you? Are you following it? Just give confirmation quickly so that we'll move ahead. Excellent, excellent. Great, great, great. So I think it's clear to you. It's clear to you, right? Now, as we move ahead, if we move ahead, then we can discuss about the reverse bias of the diode. So when we reverse bias the diode, so what do we know? So when we reverse bias the diode, depletion region inside the diode would going to increase, and now new depletion region, it would be the factor of root of VBI plus VR, right? So I think this equation is clear to you, where we can consider depletion width increases, and definitely it gives rise to your reverse breakdown voltage. So you can even calculate with the help of VBI plus VR 1 half Emax XBR. With this formula, even we can calculate reverse breakdown voltage, right? Is it clear to you? So I hope it's clear to you. So now let's move ahead with the capacitance. Capacitance is inside the diode. So we have two capacitance over here. One is diffusion capacitance and the other is a transition capacitance. So if we talk about diffusion capacitance, so in case of the diffusion capacitance, how to remember this? How to remember this? So we know that, what do we know? So do we know Q is equal to CV? Do we know Q is equal to CV? Yes, we know this. Do we know for the capacitor, do we know I is equal to C dV by dt? Do we know this? Yes, do we know? We know this. So from this only, we can consider a diffusion capacitance. Diffusion capacitance, it would be tau I upon eta Vt. Where eta is what? Eta is a utility factor. It is 2 for silicon and it is 1 for germanium. So to recall or to remember this equation of a capacitor is going to play a very important role. If you recall this, then it is easier for you to solve any of the question based on the diffusion capacitance, right? Is it clear? Next, if we talk about, then we have a transition capacitance. It is quite simple, which is what it is. Capacitance per unit area. It is given as epsilon silicon upon XDR. Depletion width in the reverse bias, and we know that depletion width in the reverse bias is proportional to VBI plus VR, and hence transition capacitance is proportional to 1 by root of VBI plus VR, right? But now if I ask you a very simple question, which one has a higher value? Diffusion capacitance as well as a transition capacitance. So are you able to identify which one has the higher value? Diffusion capacitance and transition capacitance, which one has the higher value? Which one has the higher value? Good, good, good. CD has the higher value. CD has the higher value because depletion width in the forward bias. Depletion width in the forward bias, it is always less than the depletion width in the reverse bias. So as distance increases, capacitance reduces, right? So I hope you have recalled all the concepts which is required to solve the questions. So let's begin with the questions. Please try to solve questions as quickly as possible so that we can even recall Mos capacitor, right? So let's begin with this. We have half an hour for diode. In half an hour, maximum number of questions we'll try to cover. So let's begin. Your very first question is on your screen. In a 3, 2, 1, go. Solve this question. And in this question, let's break out. Let's break out. You are asked to find total forward current, but what I'm trying to tell you, initially you need to tell me. Initially, you need to tell me whole current, current because of holes, as well as current because of electrons. So identify these two current components and then just let me know what is the overall current. So solve this question, take your time, recall equation instead of just copying from your book. Recall equation, because if you make mistake right now, it can be rectified. But if you would make mistakes in the examination, it cannot be rectified. So do mistakes right now so that it can be rectified. So let's solve this question. This one, Srivanitha. This one, conductivity portion. Are you asking for this question? Are you asking for this question? Okay, okay. So have you got all these quantities? Okay, okay. We'll just verify. We'll just verify. So just let me know. Is it the thing which you have which you have got? All of you are getting the same values. Okay, right. The thing is, if we talk about this, so just let me know. Is this numbers correct? Yeah. Is this number correct? Delta P at t is equal to zero point 0.1 microsecond. Is this number correct? Great. So it's at 6.3 into 10 raised to 14, right? That's great. If we talk about N, so doping is 10 raised to 17. Doping is 10 raised to 17. So if we consider over here, so what is going to happen over here? ND is 10 raised to 17. So even if we consider the whole expression, I made a mistake over here. It's a mu n. It's a mu n. So let's just solve this. If most of you have doubt in this, then let's solve this. So this would be equal to nd plus delta n q mu n plus, if we talk about this, which means initial holes which is Ni square upon Nd, Ni square upon Nd plus excess holes, it's a Q mu P. So let's begin and let's solve all these parameters, 1350 and 800. So let's solve this. I think we can neglect delta n over here, but still, let's put up all those values. Let us put up all those values so that we'll get exact answer. 6.3 into 10 raised to 14. Q, let's go for the Q. 1.6 into 10 raised to minus 19. Mobility is given as 1350 plus, I think, initial number of holes, Ni is 10 raised to 10. So initial number of holes would be, I may say 10 raised to 3 plus excess holes are 6.3 into 10 raised to 14. 6.3 into 10 raised to 14. Q as well as mu P. Mu P is given as 800, right? So just solve this question and just let me know what is the answer. Is it 21? If it is 21, then that might be the correct answer. 21. It is 800. So just let me know what is the answer. It is your exact answer. It is your exact answer. So just let me know. Sri Vanita, is it clear to you? I told you, like, no need to focus on questions. Sri Vanita. I told you to focus on the concepts. So just let me know, is your concept clear? Sri Vanita, is your concept clear? Are you able to grab the concept? How we can find excess conductivity? How we can find total conductivity? Is it clear? Okay, okay, that's fine. That's fine. Because numbers can be calculated in a wrong manner, but I think concept cannot be multiple concepts cannot be there, right? So can we move ahead, Shivanitha? Okay, 21.81. That's great. Then answer is 21.8 only, right? Then answer is 21.8 only, right? So I think whoever has told me yesterday, answer of 12 might be. That might be a typing error, not an issue, right? Sure. So let's move ahead and discuss the question which I have given to you. So just let me know, whole current, what is the amount of the whole current, what is the amount of the electron current. Just make it somewhat faster because we need to recall MOS also, MOS capacitor. And I think that would be the weakest point of your subject, right? So just let me know what is your whole current, what is your electron current, so that we can move ahead. Are you getting answers? Anyone has got the answer? Or are you just getting confused? Good, good, good. Is it IN? Is it IN, Srinivasa? Okay, MS Priya. IP is 9.92 into 10 raised to minus 5. IP is equal to 0.22. Okay, Srinivasa. Srinivasa and MS Priya, like you both are getting different answers. You need to be very much clear which equation you are using and from given data how you are manipulating your data. You need to be quite comfortable with manipulating your data. So if someone asks me about say current because of holes, so I straight away recall the equation of diffusion, which is nothing but dpq, which is nothing but dpq delta p by delta x, delta p by delta x. I don't recall any other formula which can relate current and forward bias. DPQ, it would be as it is. And now what do we know? If it's a DPQ, if it is DPQ, we need to go for the average diffusion length. We need to go for the average diffusion length, which is LP. Excess holes are nothing but the initial holes inside the end region, E raised to Vf upon Vt minus 1. Is it right or wrong? Is it right or wrong? If you are investing your 5 minutes then what I think your answer for this question must be correct, because in the gate examination, if you give your 5 to 10 minutes, then your this answer must be correct. It should not be like that you have invested your 5 to 10 minutes and you have got nothing out of this question. And devices is the subject which gives you 4 to 5 marks extra, which would lead to you than the average student. If you secure maximum number of marks in devices, then believe me, your rank would be affected the most, right? So here we talk about this one. Then what do you think? How can we approach this data? Whatever given to us from this, is it possible for us to find out DP? Is it possible us to find out DP, LP, and all these parameters? So I think yes, it is easier for us to find out DP. So my equation would be DP upon tau p, DP upon tau p, DP upon tau p, Q P n naught, Q P n naught, e raised to Vf upon Vt minus 1, e raised to Vf upon Vt minus 1. Now can you find out DP? Can you find out DP? Now if we talk about DP, so what do we know exactly? We can use Einstein relationship. Then DP is what? Mu p Vt. Mu p Vt upon tau p. Mu p Vt upon tau p, and then it would be Q P n naught e raised to Vf upon Vt minus 1. But now the thing is, this mu p and tau p, it should be in which region? This mu p and tau p, it should be in which region? As I have told you earlier, this mu p and tau p, if you take in the other region, then it may happen your answer is going to be wrong. So just reply me back. If we talk about this mu p and tau p, then ultimately in which region we are targeting for mu p and tau p? What do you think? This mu p and tau p, it should be in which region? Hello? Reply me back quickly. If we talk about this mu p and tau p, then in which region we are considering this mu p and tau p? So I think we'll consider all these parameters into the n region, right? We'll consider all these parameters in the n region. So I hope if you have applied this formula even for the n-type material, even for the n-type for the electrons, then this equation would be a root of mu n Vt upon tau n q into np naught e raised to Vf upon Vt minus 1. So now just let me know what is your answer after solving this. Now just let me know, put all the values given to you. I think you can go for Vt 26 millivolt, eta is 1. So calculate all these parameters and just let me know what is your delta P and delta N over, sorry, IP and IN over here. And then we just need to add these two components, right? So it may happen gate won't ask you a whole current, but gate might ask you a single current component, either IP or IN. So just let me know what is the correct answer over here so that we can move ahead with the next question. Have you used the same formula? Have you used the same formula, MS Priya and Srinivasa? Have you used the same formula? Okay, okay. So just give me your answers. Just okay, okay, Srinivasa. Just give me your answers. IP and IN. Srinivasa. Share your answers. Okay, we need answers in microampere. We need answers in microampere. So according to Srinivasa, I think answers are 18 microampere and 2 microampere. Is it so? Is it so, Srinivasa? Okay, okay, it's a micro only. That's great. That's great. So I think what answer you are getting is zero point 0.0. It's 0.018 microampere. It's 0.018 microampere. And this would be 0.02. 0.002 microampere. So just everyone verify this. Is it the correct answer? Is it the correct answer? Everyone just verify this. And if it is so, then I can consider our total current ID, total current would be addition of these two current components, which would be 0.020 microampere. Is it so? 0.020 microampere. Is it so? Just to verify this, just to verify this, it's okay. Srinivasa, it's okay. Minus one you can neglect. Minus one you can neglect. That's perfectly fine. Have you considered this voltage, applied voltage 0.5? 0.5 divided by Sri Vanitha, E power is getting as infinite. Vanitha, how can that be possible? It's a E raised to applied voltage would be 25. Sorry, zero point 0.5. Zero point 0.5 divided by 0.026. 0.026. So if I just calculate this term, so it would be, just give me a second. It's 0.026. If we go for E raised to, it's a 2.25 into 10 raised to 8. Just to verify, it's a 2.25 into 10 raised to 8. That's what I'm getting. It's a 2.25 into 10 raised to 8. That's what I'm getting right now. So just to verify, is it so? Don't make mistakes in calculation. Don't make mistakes in calculation. You must be pretty much clear with the calculator. Is it so? Is it so? Just give confirmation. Are you getting answers? Are you getting answers? 0.026, it's my mistake. It's my mistake. It's a 0.026 volt. It's a 0.026 volt. Sorry. It's my mistake, Sri Vanitha. I think that must be clear to you. It's not milli. It's not milli. You know that it's 26 millivolt. It's just a printing mistake. It's a writing mistake. It is 26 millivolt, right? So now I hope these answers are correct, Srinivasa. I hope these answers are correct. So let's go for the next question. Let's go for the next question, or verify with these answers, or verify these answers quickly. Right? Is it correct, MS Priya? MS Priya, is it correct? No. How can we neglect NP naught? No, 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 dear. No. How can you neglect the NP naught? Like if you consider in n-type material we must be having Pn naught. In n-type material we must be having Pn naught, and this Pn naught would be Ni is 1.5 10 raised to 20 and 10 raised to 15. This would be, I can say, 2.25 into 10 raised to 15, not 10 raised to 15, it is 10 raised to 5. If I consider for the p-type material, then for p-type material we would be having np naught, where np naught is equal to 10 raised to 17 and this, so it will be 2.25 into 10 raised to 3. How can you neglect that, beta? You can't neglect this. You can't neglect this, and you need to consider this, and then only you will get the correct answer. So just reply me back. Now, are you getting the correct answer? You can't neglect, right? You can't neglect, right? Okay. So shall we move ahead? So shall we move ahead with the next example? Okay. So let's solve the next example. I hope this example, concept of this question is clear to you. Concept of this question is clear to you. Calculation you will do it by yourself, right? So let's begin with the next question. So in 3, 2, 1, go. Solve this question. It is a really simple question, and I hope this could be solved by all of you. It is a really simple question. Now just let me know, are you able to solve this question or not? It is a really very simple question. It is a very really simple question. Good, good. Rajshekara. Good, good. Srinivasa. Good. It's a 0.55. It is 0.55 volt. Excellent. It is 0.55 volt. A very simple question and a straightforward question. What do we know here? A P plus N junction has depletion layer width at a reverse bias voltage of a minus 3 volt is 8 microsecond. 8 micrometer. For the reverse bias of the minus 5 volt, it is incremented by 25%. So, a very first thing what we know that the depletion region in the reverse bias region is a proportional to what? It is a proportional to built-in potential VBI plus applied reverse bias voltage. So we can go for the modulus of the VR, right? Because and only width increases. Now you just need to go for the ratio over here. Now if you go for the ratio over here, so I think you would get your answer, right? Is it so? Is it so? So I hope most of you get the value of I can say not new, built-in potential. It should be 0.55, right? So I hope it's clear to you. Nothing rocket science is there. It's a very simple question where you just need to have a ratio of two different depletion regions and for two different reverse bias voltages, and you need to find reverse bias voltage. Is it so? Is it so? So I hope it's clear to you. I think concept is clear to you and you will be able to solve the question, right? So I'm moving ahead with the next question. So let's discuss this question. Think about it and solve this question. It is again a very simple question. Okay, Srinivasa, 3.6 kilovolt per centimeter. So let's see what others are saying. Let's see what others are saying. Just solve this question very quickly. Solve these questions very quickly. Where do people stuck? Where do people stuck? Srinivasa, Srinivasa, VBI is not given to you, but can't you find it out? VBI is not given to you, but can't you find it out? Because if we talk about VBI, then what is VBI? If we talk about VBI, then VBI is what? It must be clear to you that VBI is equal to thermal voltage VT ln NAND upon Ni square. Do you know this? It's a NAND upon Ni square, right? So by using this formula, you need to find a built-in potential, right? That's right. Now what I'm telling you, where you people are having problem, just let me know. Are you not able to apply concepts over here? Are you not able to apply concepts over here? Just let me know so that we'll discuss that how to think a question before solving it. Are you people facing a problem with that? Like how to apply concepts in the question? Are you people facing problem with that? Okay, that's great. So I think there is a problem with the thought process. So just let me know if I talk about say a PN junction diode with a Na is equal to something, Nd is equal to something, a reverse bias voltage is applied, then the magnitude of the maximum electrical field at the junction. So first of all, if anyone asks me to solve this question, Srinivasa, it won't affect your answer. But the thing is, if it won't be in the range which is given by the gate, then your answer would be wrong. So no need to neglect 0.6 because of 4 and 4.6, it would affect somewhat your answer. If it is not in the range, then you would be given 0 marks, right? So here, what I'm telling you, I'm just telling you to approach, like how you should approach any of the question. So here, if I'm talking about, I'm asked to find maximum electrical field. So just answer small questions. Whenever you approach any of the question, answer small questions that which formula is going to be applicable over here. So very first question which you should ask over here, when we apply reverse bias to the junction, what would happen to the electrical field? So can you answer this question by yourself? When we apply reverse bias to the junction, reverse bias to the diode, what would happen to the electrical field? Is it going to increase or it is going to reduce than the open circuited diode? So what do you think? When we apply the reverse bias voltage, what would happen to the internal electrical field? Is it going to be incremented? Internal electrical field, is it going to be incremented? And that's why it is not allowing majority charge carrier to diffuse. Majority charge carrier to diffuse, right? So if we consider that electrical field increases, so if electrical field increases, then what happens with the internal potential? Electrical field increases, then what happens with the internal potential? It also increases. Depletion width increases, which means ultimately, if we talk about this question, then I need to find Emax. I need to find Emax, and what do we know? We know that applied voltage, VBI plus VR, this would be again what? This would be again what? It is half of magnitude of Emax, into depletion width in the reverse bias. Is it correct or not? Is it correct or not? Right? If it is, if you still can't recall this, then my advice would be, you should remember everything in terms of the graph. You should remember everything in terms of the graph. Graph in the sense, just let me know, are you able to draw graph for, the electrical field inside the unbiased diode? Can we draw electrical field, or I may say mode of electrical field inside the unbiased diode? So if we draw this, then what do we know? There must be some finite electrical field. There must be some finite electrical field with some depletion width, right? We have a maximum electrical field at the junction. Ultimately, here also, if we consider area under this curve, then let me know this quantity would be equal to what? This quantity would be equal to what? Do we know this? If we integrate electrical field curve, then what we are going to get? Integration. If we integrate this, then what we are going to get? Which quantity we are going to get? So you must be clear. Exactly, we would be getting internal potential. Which is VBI. It is nothing but half of Emax. It is nothing but the half of Emax into depletion width. Is it so? Yes, sir. It would be Emax into depletion width. But now just let me know what happens if we apply reverse bias. Then if we apply reverse bias, depletion width increases, as well as what increases? As well as we can consider what? Maximum electrical field inside the material, it also increases. And if maximum electrical field inside the material increases, then hence here too, what we are going to get? We are going to get VBI plus reverse apply voltage, which would be nothing but half of Emax new, which we are getting for the reverse biased diode, and we need to consider XD even for the reverse bias. Is it so? Are you following this? Is it so? Are you following this? Now question has become quite simpler. Now question has become quite simpler because what we need to find, we just need to find XDR. We just need to find XDR. And do you know how to find XD in the reverse bias? Do you know how to find XD, depletion region width, in the reverse bias? I hope it is very much clear to you. How do you find this? You find this with the twice of epsilon silicon, VBI plus VR, VBI plus VR divide by Q, whichever is less you can consider, but it's okay. If you want to find it properly, then it would be 1 divided by Na plus 1 divided by Nd. Is it so? Is it so? Are you following this? Are you following this? Is everything given to you? Yes, everything is given to you. Everything is given to you. So just let me know. Are you able to find out its value? Like if it is not given to, if you want to find even epsilon naught, then epsilon naught is given as, it is given as 8.85. It is 8.85 into 10 raised to minus 14, 10 raised to minus 14 farad per centimeter, right? So let's take all these values and find out the maximum electrical field at the junction. So Rajashekhar, is it 39? Is it 39 what we are getting right now? Is it 39 what we are getting right now? Is it so? Okay, just everyone verify this. Is it 39 kilovolt per centimeter? Just to verify very quickly. Is it 39 kilovolt per centimeter? Just to verify this. Is it so? What everyone is getting? Is it so? All of you getting it as 39? Everyone is getting it at 39? Good, 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 good. So let's discuss the next question. Let's discuss the next question. Just be very quick. Let's discuss this question. Okay, Srivanitha, are you getting 63 for the previous question? 63K for the previous question. Okay, Srivanitha, just go through your calculations once. Just go through your calculations once. I hope you have used the same formulas over here. I just put values over here so that it would be easier for you to get the correct your answer. I just put values over here. 2 into epsilon silicon is 12 into it's 8.85 into 10 raised to minus 14 VBI. I think it is zero point 0.6. It is zero point 0.6 plus 4.5. So I think it is 5.1. If I am not wrong, it's a 5.1. So it's a 5.1 divided by Q 10 raised to minus 19, and this would be 10 raised to 15 and 10 raised to 16. This would be 10 raised to 15 plus 1 divided by 10 raised to 16, right? So just verify Sri, what's your good name? Sri Vanitha. Is it the quantities what you have put across? These are the numbers you have put across. Okay, okay. So just verify once and just let me know. Is it the same? Okay. So just verify. I may say Rajasekhar and Srinivasa. What is the depletion width for the previous question? What is the depletion width for the previous question? What are you getting? Depletion width for the previous question. What is the depletion width for the previous question? Okay, 2.7 micrometer, right? 2.7 micrometer. So I think it would be 5.1 is equal to 1 by 2 Emax, and XD in a reverse. What we have got, it is 2.7 micrometer, which would be, I can say, 10 raised to minus 4 meter, 10 raised to minus 4 centimeter. So Sri Vanitha, just verify all these quantities. What's your answer? What is your answer for Emax? Just calculate it. Great, great, great. It is 39K. Sri Vanitha, it is 39K. It is not 3.9. You will get into 10 raised to 4. You will get into 10 raised to 4. So I think 39 is the correct. Right. Okay. Okay. Done. Right. Chal. Solve this next question quickly. Any one of you got the answer for the next question? Any one of you got the answer for the next question? Anyone got the answer for the next question? It is a really simple question. Just let me know. Have you got the answer? Have you got the answer for the question? Okay, Srinivasa, up first, you are stuck. Okay, let's discuss this. Let's discuss this. So if I talk about a PN junction has a cross-section area of 1.5 micrometer square with the ND is very larger than NA and the conductivity in the P region is 0.45 microcentimeter inverse. If the built-in potential is 0.5 volt, reverse bias voltage is 5 volt, junction capacitance is how much? So first of all, can anyone tell me which equation can be used over here? Which equation can be used over here? Can anyone tell me which equation can be used over here? We need to find junction capacitance. So I think equation is quite simple. We need to find transition capacitance. We need to find transition capacitance, which is nothing but epsilon silicon A by D, which is epsilon silicon into A by D, where D is what? Depletion width in the reverse bias, right? It is XD in the reverse bias. But now the thing is, you are not given the direct depletion width. And even what do you know, which are the quantities which would be required over here? You need to find, or you need to have XD depletion width in the reverse bias. It is the thing which you need. So how to find this? So you have formula for this. You have a formula for this, and that formula is what? It's a twice epsilon silicon. It is twice epsilon silicon, and it is a reverse bias. It would be VBI plus VR. It would be VBI plus VR divided by Q, and this would be 1 upon Na plus 1 upon Nd. 1 upon Na plus 1 upon Nd. So now just let me know what can we neglect if it is 1 upon Na and 1 upon Nd. So just let me know what can we neglect if Nd is very large than Na. It is given to you that Nd is very large than Na. Then what do you think? What can we neglect? Right? We can neglect Nd over here. We can neglect Nd over here, and hence our formula would become, twice of epsilon silicon, VBI plus VR, and now this would be QNA. But again, Na is not known to us. If Na is not known to us, then it is given something. They have given something, conductivity of the P region. So do we know equation of conductivity? Conductivity of P region, it is given as what? It is given as NAQ mu P, right or wrong? NAQ mu P. So from this, you would get the value of Na. Is it right or wrong? Are you following this? I'm just trying to cover all the parameters so that it would be easier for you to recall concepts. Are you able to recall concepts? You need to find conductivity. You need to find number of doping with the help of conductivity, and hence, if you use this formula, I think you will be able to find the Na. If you have Na, you will be able to find capacitance. Is it so? Is it so? Are you following it? Is it so? Are you following it? Is it clear to you? Are you following the process? Are you following the process? That's great. That's great. I hope you are following the process. So if it is so, just let me know the answer. What is the answer for this question? What is the answer for this question? Okay, Rajshekara, it's 31.7. So let's see what else are saying. So is it the answer which everyone is getting? So is it the answer which everyone is getting? 31.8. That's great. That's great. So I think it is the answer which everyone is getting, which is 31.8, right? That's the answer which everyone is getting, which is 31.8, right? That's great. So now let's discuss MOS capacitor. There are a few questions. There are a few questions which I am leaving right now because we need to discuss even MOS capacitor, and MOS is the ultimate thing which we need to learn. So I hope you all of you are ready to learn MOS capacitor. It is something which is the weakest topic of everyone. I think it is the weakest topic of everyone. So can we discuss that for next half an hour? Can we discuss that? All of you are ready? I am just going to discuss concepts because I am not going to discuss questions of MOS capacitor in this short time. So just get ready with get ready. We'll discuss concepts. BJT, it is a mainly part of say analog circuits. So Srinivasa, it would be covered over there. From devices, it is not asked much about the BJT. So let's discuss MOS capacitor. Just have focus for next 30 minutes. because I discussed important parameters of MOS capacitor, which is a very difficult topic of devices. So as we talk about the MOS capacitor, we know that we have a structure, which is metal, oxide and semiconductor. If I talk about the semiconductor, then for the semiconductor, we have a concentration. Let's consider the semiconductor to be of the P type. Then what do we know for the P type semiconductor? We have majority holes and minority electrons. So it is a charge distribution, charge carrier concentration on the log scale inside the P type substrate, where we can consider we have majority of holes and minority of electrons. We have considered an example of holes to be 10⁻16. So approximately our electrons will be 10⁻14 in a number. At the same time, what I am drawing, I am drawing energy band diagram. So we can consider that in case of the energy band diagram, what do we have over here? What do we have over here? We have a p-type material, that's why it has a Fermi level which is below the intrinsic Fermi level, right? So if I consider topics over here, so I am going to integrate all these three diagrams. I am going to integrate all these three diagrams: actual diagram of MOS capacitor, carrier concentration inside the material, as well as energy band diagram, right? Now, if we talk about relative shift over here, relative shift is known as a surface potential. Relative shift is also known as surface potential for the MOS capacitor, and it is known as what? KT ln Na upon Ni. Do you know this? Relative shift, which means difference between material's Fermi level and intrinsic Fermi level. So in case of the MOS capacitor, it is nothing but the kT ln Na upon Ni, and if we consider Na, where Na is nothing but number of holes inside the material, which is known as the kT ln number of holes upon Ni. And as you can see here, right now I am considering an ideal MOS capacitor which has a flat energy bands, and that's why this condition is known as the flat band inside the material. It's also known as the flat band inside the material, right? So just keep this thing in your mind, that what I'm talking about number of holes inside the material, number of electrons inside the material, as well as material's Fermi energy level, material's energy band diagram. I am considering these two diagrams at the same time. Now let's discuss what happens if we apply voltage to this material. Now if I apply a negative voltage, then what do you think? Now if I apply negative voltage to this MOS capacitor, then what happens? Negative charges are going to be accumulated on the metal terminal. Negative charges are going to be accumulated on the metal terminal. Now to compensate this negative accumulation of charges at metal inside the substrate, I can say oxide semiconductor boundary, there must be accumulation of equal and opposite charge. There must be accumulation, there must be pile up of the equal and opposite charge. So if we look at the picture, then if in the metal we have negative charges, then in the oxide semiconductor boundary, we must be having the same amount of the positive charge. And this positive charge, from where this positive charge comes from? So as we know that it is a p-type semiconductor, and in case of the p-type semiconductor, majority charge carriers are holes. And those holes are nothing. Those holes are going to contribute this positive charge, which is required to compensate negative charges which have accumulated at the metal terminal, right? So now if we look at the charge picture over here, so negative charge is there in the metal boundary, and if we consider positive charge, it has piled up near the oxide semiconductor boundary. Now just let me know, if we talk about this piling of the positive charge, then this positive charges has to distribute at the boundary. And that's why they are going to form a capacitor. Can you feel that? Can you feel that? We have piling up of the negative charge carriers over here at the one side of the oxide layer, and accumulation, or I can say piling up of the positive charge carriers on the other side of the oxide layer, and ultimately it creates what? Ultimately it creates a capacitor. Ultimately it creates capacitor inside the MOS. Are you able to look at that? Right? And now if we look at the electrical field, so I told you earlier, to get the electrical field we need to integrate charge distribution. So we have negative charges over here, we have positive charges over here. Now if we integrate this, then we would be having, we can consider these charges as impulses. Impulse of negative charge, impulse of a positive charge. If we integrate this, then we'll get a step function. We get a step function, and ultimately we would have a constant electrical field inside the oxide. Is it so? Are you following this? It is just like your parallel plate capacitor. It is just like your parallel plate capacitor where we have two plates, and whole electrical field is confined between these two plates. In this parallel plate capacitor, we have negative charge on the one plate, we have positive charge on the other plate, and the whole electrical field is confined between the between the plates. Is it so? Is it so? Are you following this? Are you following this? What I am trying to convey to you, we have two plates. One is negative charge, one is positive charge, and because of that reason, electrical field is confined between these two plates. So we have here what we have. We have drop across. We have electrical field across oxide layer, and if we integrate this electrical field, we are going to get drop across the oxide, and it is ultimately what? It is ultimately represents whatever negative voltage we have applied across the MOS capacitor. Is it clear to you? Ultimately, if we the sequence is quite clear. I think sequence should be quite clear. If we integrate charge and divide it by the epsilon silicon, we would get electrical field. If we integrate electrical field, we'll get a voltage, right? So now the thing which you should remember over here is inside the MOS capacitor, a whole voltage is going to be dropped across the oxide. The whole voltage drop is going to be take place across the oxide layer because the electrical field is confined between two plates. But now if here we consider the charge carrier inside the p-type material, then we can consider that, we can see that we have piling up the holes at the oxide semiconductor boundary. We are going to have the piling up of the holes at the oxide semiconductor boundary. If holes increases, number of electrons decreases, and this process is ultimately known as accumulation. Why accumulation? Because we are piling up, we are gathering majority holes at the interface, right? We are piling up majority of holes at the interface, and that's why this process is known as the accumulation of majority charge carriers. Are you following this? Are you following this? Till now, is it clear to you? Till now, is it clear to you? Maximum number of times, student has a confusion about the energy band diagram. Student has the confusion about the energy band diagram. So now just let me know, if I talk about the energy band diagram, then do we know relative shift? Do we know equation of relative shift? Now what is relative shift? And initially just let me know what do we mean by the relative shift. So I can consider relative shift is what? Relative shift is what? It is a separation. It is separation between materials Fermi level and intrinsic Fermi level, right? It is separation between materials Fermi level and intrinsic Fermi level, and it is a function of what? It is the function of carrier concentration, majority carrier concentration. So now just let me know, if we consider over here, then we have concluded that number of holes at interface increases. Number of holes at interface increases, and as holes increases, what do you think? Separation between materials Fermi level and intrinsic Fermi level, is it going to increase or decrease? We are saying over here that number of holes at interface increases, which means relative shift between Fermi level at interface, is it going to increase or decrease? So absolutely it is going to increase. Are you able to look at that? Are you able to look at that? This is the bulk region. This is the bulk region, and this is the interface. It is the boundary. So as you approach boundary, in the energy band diagram, relative shift is increasing. Is it so? Is it visible to all of you? As we move towards junction, relative shift between materials Fermi level and intrinsic Fermi level, it is increasing. Is it visible to all of you? And if it is visible to all of you, you can comment from here that accumulation process has occurred. No need to mug up this. Because if you mug up this, then you would be in a trouble, because you won't remember which process indicates accumulation, which process indicates surface inversion, and vice versa. Are you able to grab this? First of all, to identify the process, you need to identify which kind of material you are having. Is it of the N-type material or the P-type material? Now, how do you comment that? If material's Fermi level is below intrinsic Fermi level, then material would be P-type, and if material's Fermi level is above intrinsic Fermi level, then material would be N-type. So this material is a P-type, and what you can consider, from bulk compared to bulk, we have larger separation at the boundary. If it is so, that means number of majority charge carriers has increased, which means holes has increased, and that's why this process is accumulation. Are you able to comment this? Would you be able to comment this, or should I repeat this? Are you able to connect this? Are you able to comment this? Right? It is a very simple thing, but you just need some small observation, and that observation is, if number of holes at the interface increases, which means there is a process of accumulation, and number of holes would increase, right? Now, what if, now here, if we need to find the charges, number of charges which have accumulated, so how can we find? This accumulated charges are known as the accumulation charge, and this accumulation charge you can find with the help of Q is equal to CV. You can find this accumulation charge as Q is equal to CV. But now the thing is, just let me know what is the voltage which we have applied. I think if it is clear to you that we have applied negative voltage. We have applied negative voltage, but charge what we are having is a positive, and that's why we need to put an extra negative sign over here, right? So I hope it's clear to you. Q is equal to CV. It is accumulation charge, and where C is what? Eox upon Tox, right? So it is the thing which is happening if we apply the negative voltage. Now let us consider what happens when we apply the positive voltage. Now let us consider what would happen when we apply the positive voltage. Now when we apply the positive voltage, now look at this very carefully. Now when we apply the positive voltage, what would happen? Piling of positive charges would occur in the metal end. Positive charges would accumulate at the metal end. And now what would happen? Here we need to have negative charges at the interface. At oxide semiconductor boundary, we must have negative charges. But now tell me, negative charges in the P-type material is going to be provided by what? The negative charges in the P-type semiconductor is going to be provided by what? Exactly. Initially, depletion would take place, but if we consider for the N-type material, for the P-type material, then negative charge can be provided by either atoms, either ions, or electrons. Is it so? Do you know equation of the charge neutrality? Do you know the equation of the charge neutrality? It says Nd plus P is equal to Na plus N. Right? It is Nd plus P is equal to Na plus N. Initially, Yamini and Srinivasa, initially battery is not having that much capacity to have electrons over here. It is not providing maximum, it is not providing that much number of electrons. So initially what is going to happen in case of p-type material, we are having to have a negative charge. It is either because of negative immobile ions or because of minority electrons. But initially negative charge is going to be provided by the depletion charge, and this depletion negative immobile ions are going to be there by removal of holes from the region, by removal of holes from the interface. Holes are going to be removed from the interface, removed from the oxide semiconductor boundary, and if these holes are moving away, they would leave behind negative immobile ion. Is it so? If these holes are moving away from the oxide semiconductor boundary, they would leave behind negative immobile ion. And now just let me know, this negative immobile ions, are they going to be piled up at the interface? Are you be able to move this negative immobile ions from their lattice? Are you be able to move this negative immobile ions from their lattice? Huh? We can't move, exactly, we can't move this negative immobile ions from their lattice, and that's why there would be creation of depletion region. There would be creation of depletion region at the oxide semiconductor boundary, at the oxide semiconductor boundary, right? And now if we consider this charge, if we integrate this, then this would be a ramp function. This would be a ramp function which would give us the electrical field. Which would give us the electrical field. So now the thing is, if we integrate this charge, which is depletion charge, and divide this by the epsilon silicon, we would be given an electrical field inside the material. And as this electrical field is perpendicular, to the oxide semiconductor boundary, we should apply a boundary condition. And if we apply boundary condition, normal boundary condition, then your electrical field is what? Your electrical field is what? We can consider that normal component of electrical field density is equal where surface charges are not present. So we can consider epsilon ox into E ox is equal to epsilon silicon into E silicon, and hence we can consider electrical field inside the oxide. It would be 12 by 4 electrical field inside the silicon. So I can say 3 times larger, approximately 3 times larger electrical field is there across the oxide layer. Are you able to get this? What I am trying to convey? Are you able to get this? If we find maximum electrical field inside the substrate, because if we integrate this charge, then tell me, where would you have your maximum electrical field? Because if we start integrating this charge from right to left, if we start integrating this negative charge from right to left, then because of this negative charge, we would be having a maximum electrical field. At the interface. maximum electrical field what we are having at the interface, three times of this would be in the upside. So what is your conclusion over here? Whatever positive voltage we apply across the MOS capacitor, whatever positive voltage we apply across the MOS capacitor, maximum of that applied positive voltage drop across which material? Maximum of voltage what we have applied is dropping across which material? It is dropping across oxide layer or substrate layer? Exactly, it is maximum. It is maximum drop occurs across the oxide layer and a slight drop across substrate layer, right? So what you should remember, if you integrate electrical field, you would be given psi-ox, where psi-ox is a drop across oxide layer and psi-s is the drop across the substrate layer, right? Now, if we consider this, if we keep on increasing this voltage, then what is going to happen? Now, what is going to happen for the same applied voltage? Number of holes are reducing. Number of holes are reducing because they are moving away from the interface, leaving behind the negative immobile ions. And as you have correctly said, Priya and Srinivasa, that battery is going to give electrons. So now what would happen? Electrons are going to increase in the number, but still they are not in that position to take over negative charge. To take over negative charge from electrons from holes, right? So now what is going to happen over here? As we talk about the electrons over here, then electrons are going to increase. Number of electrons are going to increase, but the thing is, what would happen? They are not in the number. They are not majority in the number, so that they can provide negative charge compared to the negative immobile ions. But now, if we consider the energy band diagram, then what would happen with the energy band diagram? Energy band diagram. So what we can consider as holes are moving away from the interface, number of holes at the interface decreases, and hence relative shift also decreases. Relative shift is also decreases. Are you able to follow this? And hence you can consider, but still, just let me know. At interface also, material is N-type or P-type. If we consider this, then just let me know, even at interface, material is N-type or P-type. Just let me know. Material, is it of N-type or P-type? Although number of holes are reduced, number of holes has reduced, but let me know, material is still N-type or P-type? It is P-type. It is a P-type, but it is less P-type compared to the bulk region, and hence this process is known as the depletion process. As we keep on increasing voltage, what would happen? As we keep on increasing voltage, number of electrons keeps on increasing. We would have a condition where number of electrons are equal to number of holes, which means material has become intrinsic. Energy band diagram, in that case, materials Fermi level and intrinsic Fermi level, they both coincides. And what happens as we keep on increasing, at some point of time, what is going to happen? Number of electrons in the material is same as the number of holes in the bulk, and at that time we have a movement of energy band diagram of what we can consider, whatever material we have in the bulk, P type, exactly same amount of we have conversion at the interface, which means Here material is p type, here material is n type, but it is exactly equal in a proportion. It is exactly equal in a proportion, which means whatever amount of p holes we are having here, same amount of electrons we are having over here, and that's why this process is known as inversion. And when inversion takes place, we have the highest bending of the region. We have highest bending of the energy band diagram, which is twice of phi f, which is given as what? Which is given as of VT ln doping. It's a relative shift Na upon Ni, but now it is of the twice. Are you following this? Twice of VT ln Na upon Ni. Twice of VT ln Na upon Ni, right? Why twice? This is the relative shift for the p material. It is the relative shift for the p material. We have done twice of bending to achieve the n material, right? So it is the maximum drop. It is the maximum drop across the substrate layer. It is the maximum drop across the substrate layer. And if we want to find the threshold voltage, then for the threshold voltage, what do we have? For the threshold voltage, okay, just let me know in this which kind of process has been occurred. Can you identify which process has occurred over here? Depletion, accumulation, surface inversion. Which process has occurred over here? Think about it. Which process has occurred over here? Look at the energy band diagram. And then comment which process has occurred over here. First of all, just let me know it is a which kind of semiconductor. It is a which kind of semiconductor. No need to mug up. That's why I have been telling you, no need to mug up. Just let me know which kind of material is this. It is n type. In n type of material, what do you think? Relative shift has increased or decreased? In n type of semiconductor, relative shift has increased or decreased? Relative shift has increased or decreased? As you approach a junction, as you approach a boundary, what do you think? Relative shift has increased or decreased? Decreased. If relative shift has decreased, then just let me know what has happened. It is an n-type material. If relative shift has decreased, then number of electrons has increased, number of majority charge carriers has increased or decreased? Relative shift decreases, then what is going to happen over here? What do you think? Number of majority charge carrier decreases. No, Srivanitha. Relative shift is a function of majority charge carriers. If majority charge carrier decreases, relative shift decreases. Now, if relative shift decreases, majority charge carrier decreases, that means this process is what? Which means this process is what? It is depletion. Why it is depletion? Why it is depletion? Because still material is n-type. Surface inversion has not taken place over here. Still material is n-type, but number of electrons are less compared to bulk, which means they have left the oxide region and positive immobile ions has been disclosed over here. Are you able to get this? So to comment accumulation, surface inversion, strong inversion, weak inversion, you need to see material and its it's a relative shift. If you are able to get that, you can comment answer properly. Is it so? Is it so? Right? I think it's enough for this. You can even have a look at the voltage. You can have the look at the equation of the voltage. So I have a page. I have a single page where I have equations. So just look at this. Just look at this equations. Psiox drop across oxide. It is electrical field across oxide, and Tox. Psi S. How do we find Psi S? To find the Psi S, we have 1/2 ES XD. Maximum drop across across oxide layer, across surface. It is twice of relative shift. We can find ES. We can also find electrical field maximum by integrating charge. It's a QNA XD epsilon silicon, with threshold ideally is Psiox upon Psi S, and Psiox is what? Eox upon Eox into Tox, twice of Phi S. And to find Eox, we can have two methods. We can have two methods, which is written over here. So I think just go through it. It would be helpful to you to recall. So I could not, we could not solve questions, but I think this would be helpful for you to recall MOS. So again, I hope you have enjoyed this. You have enjoyed this. We could not solve questions of MOS, but it's okay. Solve those questions by yourself. Notes, I don't know. I can share or not. I don't know. I can share notes or not. But if it is possible, I'll share. So I hope you have enjoyed this. I hope you have enjoyed this. So thank you so much for being with me for four hours. I hope I have covered most of the topics, and it would be help you out to prepare well for your subject. So thank you so much for being with me. All the best for the GATE examination. Prepare well. Use your time well. Thank you so much. Thanks for being such a nice audience. It's my pleasure to be with you. Thank you so much.